Okay, so today we're going to talk about a couple of important properties of the center of mass of a system. And the center of mass is defined by the equation on the board here. It is the weighted average position of all the masses inside a system. And so that's actually one of the important properties that we need to understand. This is a weighted average position. A second important property is when we have a system composed of masses that are located at different places, this center of mass has a special property that we can describe the motion of that system as if the entire mass of the system were concentrated at that one single position, the position of the center of mass. And so one way I want to demonstrate that, I have a meter stick here, and a meter stick has mass at lots of different positions, but because it has uniform density, equal mass per centimeter along the stick, the center of mass of a meter stick is at the center of the meter stick. And I'm going to demonstrate that simply by balancing this meter stick on its center of mass, which is at the 50 centimeter mark. So making a list of the important properties that we've just mentioned. Number one, the center of mass position is a weighted average of all the positions of all the masses composing a system. An example would be this meter stick here. Its center of mass is at the average position of all the mass, which is at the 50 centimeter mark. A second important property is that we can imagine all of the mass of this system to be scrunched at that one point, the 50 centimeter point in this case, at the center of mass. A third property that I'm demonstrating right now is that a system is going to be balanced if it's supported underneath its center of mass. So right now my finger is directly under the 50 centimeter mark, and you can see that this system is in a stable equilibrium. It is balanced. If I were to try to support it at any other point that's not directly underneath the center of mass, it's going to topple. All right? So that has lots of important applications as well. I want to do one more example. So here I have a meter stick that has some extra mass taped on it. And you can see that this has some mass. It has 200 grams taped on at about the 80 centimeter mark here. All right? Now, that means if I consider this new meter stick as a system, its center of mass is not going to be at the 50 centimeter mark. So we're going to actually calculate right now where is the center of mass of this new system. So we're going to think of this system as having two parts. I have a meter stick, and the mass of that meter stick, I'll call M1, is 97 grams. The mass of the extra mass that I've taped on is 200 grams. All right? Now, if we want to calculate the position of the center of mass of that entire system, we need to know what are the positions of those masses relative to an origin or coordinate system that we define. So on my picture here, here's a meter stick. Here's the x equals 0 position. All right? Here's x equal to 50 centimeters right there. And out here is x equal to 80 centimeters. So what would I put in for the positions of these two masses? Well, like we were talking about a minute ago, when I think about just the meter stick itself, I can pretend like the entire mass of that meter stick is concentrated at the 50 centimeter position, because that is the center of mass of this object. So x1, the position of that meter stick is going to be 50 centimeters when I determine the center mass of the larger system. x2 is going to be the position of the second mass. That's going to be at 80 centimeters. All right. If I put those together into this formula, to my weighted average, I'm going to take 97 grams times the position of that mass, which is 50 centimeters. I'm going to add 200 grams times the position of that mass, which is 80 centimeters. And I'm going to divide by the total mass, 97 grams, plus 200 grams. And if you calculate that, you'll get about 71 centimeters, something like that. That is the position of the center of mass of that entire system. Now, how could we test that? Well, we can go back and use another property that's special about the center of mass. If the center of mass is at a certain place, this object will be balanced only if I support it underneath its center of mass. So I'm going to put my finger under the 71 centimeter mark now, and it is balanced when I put my finger there. So notice that by adding some mass on this side of the meter stick, the center of mass has moved from the 50 centimeter mark out to there. And so we've learned three important things about center of mass. We've learned that it's a weighted average position. We've learned that an object is balanced only if the base of support is underneath its center of mass. And we've learned that we can pretend like all the mass of a system is concentrated at that one point, the center of mass.